I will be focusing on semiconductor to metal or insulator to metal transitions, and they are of technological relevance because it would be nice to have ultra-fast switches. And of course, they should not only be switched on femtosecond timescales, but also switch back quickly on ultra-fast timescales. There are different ways to transform a semiconductor to a metal, and one is that photoexcitation can drive the system into a different structure that then also exhibits a different electronic structure. But also strong correlation effects, very strong interaction of charge carriers can lead to an insulator to metal transition. As an example, I'm showing here the phase diagram of V2O3 as a function of temperature and doping concentration, and it exhibits insulating and metallic phases. And the trick is to exchange the chemical doping by photodoping through photoexcitation. This is a very nice thought. However, it turns out that in most, if not all materials, you really need a very, very strong excitation density to drive the transition into the metallic state on the order of millijoules per square centimeter. And beyond the issue that this is not very feasible for technological applications, this also deposits a lot of energy into the system, and this heats up your sample so strongly that even when the charge carriers have decayed, you are still in the metallic phase because simply your sample is still hot. And this is why you have to wait until it cools down, and this can easily take microseconds or even milliseconds depending on your sample. There are various ways of driving also electronically an insulator to a metal, and one occurs via chemical doping as seen in the previous slide and also here. So an isolated shallow donor level can contribute to conduction in a semiconductor by thermal activation, but if you enhance the density sufficiently strongly, these shallow donor states talk to each other and you form an impurity band that facilitates metallic conduction. The density or the concentration of these donors is relevant for this transition, and of course also the effective radius of the electronic wave functions. Very closely related to this Mott transition is the so-called exciton Mott transition that occurs in photoexcited semiconductors, where you create excitons by the absorption of photons. If you excite sufficiently strongly, they start interacting with each other, and the Coulomb attraction between electron and hole is lifted, and you create an electron-hole plasma that exhibits metallic properties and shows, for example, a Drude response in optical spectroscopy. Beyond these shallow donors, semiconductors also often show deep donors that can be introduced by chemical doping or also defects. Clearly here thermal excitation is not at play, but what you can do is you can photoexcite this deep donor, and then this positive local charge creates a hydrogenic potential, and the electron can bind in this potential to form a so-called defect exciton. And I will show you today that these defect excitons actually behave very similar to shallow donors and can undergo a Mott transition. So photoexcitation creates excitons, I discussed this, and they have a binding energy that is determined by the dielectric function, so the screening in the system. In metals, this is different. You have a conduction band that is being crossed by the steady-state Fermi energy, and the free carriers at this Fermi energy contribute to the screening, lead to metallic conduction, and a Drude response in optical spectroscopy. As I mentioned, you can create such conditions also in a strongly photoexcited semiconductor, and then you form quasi-Fermi energies in the conduction and valence band. And these carriers at the quasi-Fermi energies contribute to the screening, leading to a reduced Coulomb interaction and a band gap renormalization. The band gap becomes smaller. So these semiconductors have metal-like properties, and they still are semiconductors, because what you need to really create a transient metal is that photoexcitation drives, for example, the conduction band across the Fermi level, so that you have density of states around the Fermi level and free carriers at the steady state Fermi level. Only then you have created a true metal on ultrafast timescales. And this is relevant for application, as you can see here. If you want to drive a current through a metal-like semiconductor, you still have to overcome a barrier to inject charges, which requires certain voltages. However, if you want to run a current through a transient metal, the Fermi energies align and you can directly let a current flow through the material. We investigate such phenomena using femtosecond time and angle resolved photoelectron spectroscopy, where we pump the system and then probe the dynamics in photoemission with a variable time delay. We can also independently tune the wavelength of the exciting and the probing laser beam in order to match resonances and in order to look at different regions in the electronic structure. We detect the photoelectrons as a function of parallel momentum and kinetic energy, and by that we can also determine their degree of localization and measure the effective mass of electronic bands, their dispersion. We have been looking at zinc oxide, which is a promising material because it's a transparent conductive oxide with a wide band gap. This is why it's transparent and has a high charge carrier mobility. And in addition, nanostructures are easily made from zinc oxide. However, some people might call zinc oxide nasty or at least recalcitrant, and this is because you cannot get zinc oxide without defects. In optical spectra, photoluminescence, etc., you see this strong defect band in the band gap, and this is also responsible for the yellow color of zinc oxide crystals. These defects are manifold. As an example, there are shallow donors due to zinc interstitials and also deep donors resulting from oxygen vacancies. And these are suspected to be relevant when it comes to the persistent photoconductivity of zinc oxide. So if you take a zinc oxide wire, for example, and illuminate it with UV light, you can enhance the conductivity of the sample by almost 2 orders of magnitude. And this conductivity persists even if you turn off the UV light. This is why it's called persistent. It can only be shut down by letting air into to the sample, and this means oxygen, obviously. So this hypothesis of oxygen vacancies contributing to the persistent photoconductivity is also supported by theory that calculates that the deep donor level of the oxygen vacancy is lying just on top of the valence band. However, when you ionize this level, then you generate density of states in the region of the Fermi energy, which could contribute to the conduction. So we were asking ourselves, can we maybe photoinduce an ultra-fast semiconductor-to-metal transition in zinc oxide? In order to prove that this is happening, we need to find the 3 important footprints of a metal. We need to observe density of states in the region of the Fermi energy as it's being crossed by a dispersive band, and the charge carriers in this band must follow Fermi-Dirac statistics as you would expect it for a metal. So when we do photoemission on zinc oxide, we usually plot the photoelectron intensity in false colors as a function of energy. The dashed line is always the Fermi energy in today's spectra, and as a function of emission angle. And you can already see that before time zero, before the pump pulse arrives, we see a feature with a flat dispersion. And then when we photoexcite the sample, the intensity increases significantly, and also the shape of the photoelectron distribution changes with time and becomes more and more parabolic. When we look into this and analyze this in more detail, after excitation with 3.4 electron volts resonant to the zinc oxide band gap and able to depopulate deep-lying defects in zinc oxide, we see the following time-dependent behavior as a function of pump probe delay. The photoexcitation creates electron density just below the Fermi energy, and this electron density then decays on long picosecond timescales. When we zoom in, we see that there are actually two rise times. And now the question is, how does the effective mass evolve, the effective mass of this photoinduced feature as a function of time? So we extract the dispersion of this state and plot the inverse effective mass as a function of pump probe time delay. And you can clearly see that it basically follows the evolution of the photoinduced electron density. It rises and then decays on longer time scales. So what we are observing here is a dynamic delocalization of photoinduced electron density followed by a dynamic localization on longer time scales. And this is depending on the electron density. And of course, we can also tune the electron density simply by changing the excitation fluence. You see that for low excitation fluences, we observe a flat feature in the angle resolved data, while for higher excitation densities, the feature becomes more and more parabolic. We can plot again the inverse effective mass as a function of pump fluence and fit its behavior with a critical formula, because the effective mass is the order parameter of this semiconductor-to-metal transition, just as you would expect it for an exciton mod transition and as it has been observed experimentally for chemically doped systems. And from this fit, we extract that the effective mass of the impurity band is coinciding with the effective mass of the zinc oxide conduction band, and very importantly, that the critical fluence is with 13.6 microjoules per square centimeter, orders of magnitude smaller than what you usually need to drive a semiconductor to metal transition. In addition to that, we can also look at the electron distribution as a function of energy and for different time delays and the different excitation densities. And as long as we are observing a localized electronic signature, there is no thermalization. However, once the electrons delocalize, the system thermalizes, and we can extract the electronic temperature evolution as a function of pump probe time delay, and the equilibration with the lattice has happened within the first 1 or 200 femtoseconds. So we have observed all three footprints of a metal: density of states just below the Fermi energy, a finite effective mass, Fermi-Dirac statistics. But what is the mechanism behind this? Well, I mentioned earlier the bandgap renormalization. Bandgap renormalization could drive the conduction band below the Fermi energy if we excite the system sufficiently strongly, and at the same time the valence band would shift upwards. So let's have a look in photoelectron spectroscopy what the valence band actually does upon photoexcitation. It shifts downwards. So this means there is the bandgap renormalization is not the driving mechanism of this semiconductor-to-metal transition. Instead, it's a different phenomenon, which is caused by the optical depopulation of defect levels in the bandgap. The photoexcitation leads to a very local positive charge, which then pulls the potential downwards. And this effect is well known in semiconductors. It's called inverse surface photovoltage effect. It's the enhancement of surface band bending through photoexcitation of energy levels in the bandgap and at the surface. So this would lead to a downward shift of the valence band as we observe it experimentally, and should go along with the charge density evolution just below the Fermi energy. And when we plot all our three observables, we can fit them globally and extract characteristic times. The first rise of 20 femtoseconds is likely resulting from the screening speed in zinc oxide, and the 1.2 picoseconds is likely related to the buildup of additional positive charge at the surface. It is consistent with X-ray and optical absorption experiments that show that holes are being trapped at the surface of zinc oxide on similar timescales. And then, of course, there is the decay on a 220 picosecond timescale. And this is also remarkable because this is much faster than microseconds or milliseconds of thermalization and cooling of the lattice. And the reason for this is that we do not deposit that much energy in the system, but more importantly, that hot zinc oxide is still a semiconductor. Different to the correlated electron materials where the high temperature phase is also metallic and therefore the cooling is the bottleneck for the back transition. Here we only need to get rid of the charge carrier density at the surface and then return to the semiconducting phase. But maybe you do remember that there was a signal at negative delays before the pump pulse arrives at the sample. This signal was localized and is suspiciously close to the metallic feature that we see after photoexcitation. So what can be the origin of this feature? When you have a closer look to it, it actually resembles a lot the spectral signature that we observed for chemical doping of the zinc oxide surface with hydrogen. This led to the formation of these localized electronic states just below the Fermi energy. Now, think about defect excitons. So this feature actually has a lifetime. It's not an occupied state that is always there, but its intensity depends on the repetition rate of our laser system. It's actually being reduced as we reduce the repetition rate, as we enhance the difference between succeeding laser pulses, and this is why the state has more time to decay and must exhibit a lifetime on microsecond timescales. We can formulate a complicated model of population and depopulation of the different laser pulses and fit this to the repetition rate dependence and also the fluence dependence of the signal, and then we can extract the lifetime of these defect excitons to be 77 microseconds. So do these defect excitons have something to do with the semiconductor-to-metal transition? Obviously, we can do above bandgap excitation with the UV light that we used, and with higher photon energies we can do the same, and we can also depopulate these defect levels to generate defect excitons. So now I will plot here the photoelectron intensity of the photoexcited metallic phase for different pump photon energies. For UV light excitation, clearly we observe a metallic state, and we still do observe it actually when we use 3.2 electron volt photoexcitation, which is remarkable because 3.2 eV is below the band gap of zinc oxide. So the only process that can then lead to the surface metallization is actually the depopulation of the defect level. And when we reduce our photon energy further, we realize that we can substantially reduce the intensity of this surface metal, and this is a logarithmic axis, as you can see. And this means that these defect levels must lie very deeply in the band gap of zinc oxide. Actually, it must be 3 electron volts between the conduction band and these defect levels. And this is, surprise, surprise, coinciding with the energy difference for the oxygen vacancy according to hybrid TFT calculations. So I hope I could show you that we observe an ultra-fast generation of a surface metal caused by surface photovoltage inversion through defect depopulation, which then leads to the formation of defect excitons. This transition has many nice aspects. It's reversible. It happens at an extremely low threshold fluence, and the Fermi energy of the metallic state equals the steady state Fermi level, which makes this transition really application relevant, as mentioned earlier. Also, we believe that this is not a zinc oxide specific feature because there are no zinc oxide specific aspects to it. The only thing we need is a deep defect level and an N-type compound semiconductor, and then in principle it could work. Furthermore, this transition also occurs very close to room temperature. We've done experiments up to 256 Kelvin. And with this, I would like to thank my group for the great working atmosphere. This is our group barbecue this summer. Unfortunately, not everybody could join, so the most important character of the work that I presented today is Lukas Gierster, who was the PhD student on this project, and he worked together with Zesha Vempati, a postdoc who has now moved back to India, to the Indian Institute of Technology in Bhilai.